Okay, for all technicians working on these full bridge amplifier circuit designs, you'll find this design from the likes of Sound Digital, Ground Zero, B2 Audio, Sundown Full Bridge, and Def Bonce, Alphard, etc. This is the Sound Digital copied circuit that Chinese factories are now making for many of these brands. As you can see here, this is the B2 Audio, this is the 16K, the Riot 16K. Now, the output sections of these amplifiers are sort of easy and sort of hard, and possibly a little bit scary. Now, this being a full bridge amplifier, even though it is 16,000 watts RMS, the rail voltages only are around about 200 volts, okay, which sounds like a lot. However, that is about the same as a kind of 8,000 watt RMS half bridge Korean amplifier, because full bridge amplifiers use half the internal rail voltage of a half bridge. So 16K from 200 volt rail is not too bad. But it is a little scary, and especially when you have these kind of drive circuits that are as sensitive as they are, and this kind of architecture that is very, very sensitive and very fussy with everything being perfect, you can spend a lot of money on your replacement output MOSFETs, which there are a lot of here, and they are very high current, low RDS models, and so they are pretty expensive, and you can blow them all instantly with no real way of easily checking that everything's good to go before you fit the FETs. If you're used to working on Korean half-bridge amplifiers, then a lot of the techniques that you'll be used to using don't work here with these amplifiers. So the purpose of this video is actually to give you guys some really cool methods and really awesome ways of getting these amplifiers into a state where they can be worked on and tested safely, whereby even if you still have some issues and problems in the drive circuit that you haven't fixed yet, even if there's some stuff that you missed by accident, even something as small as having an open diode across the gate resistor here, or a shorted 15 volt Zener here, for example, something that could be easily missed. If you power this amplifier up normally with 200 volt rails with all your new MOSFETs in, they would likely explode straight away. However, with these techniques, you're going to be able to power this amplifier up and even produce audio with little to almost no risk of damaging any of your new expensive parts that you've just fitted. So guys, stay tuned as we go through this. One of the things that make these so annoying to work on if you're used to Korean half bridges is the drive ICs that are used, or the drive architecture. These use an IRS 20957S. Now, unlike the IRS 21844S chips that you'll find in most Korean half bridges, you cannot get this chip to create pulses on its output legs without the MOSFETs being in place, which is very annoying. If you're used to working on Korean half bridges, you can usually power the amplifier up with all the MOSFETs removed, check that you have good looking drive waves on the low side gates, even the high side gates if you apply some voltage specifically to the high side VS or BVB, but in this case you can't. This chip will not activate without the MOSFETs in the board. There are a bunch of different pins on here relating to shutdown and enable. Pin number 2, for example. You also have pin number, I think that's 16, is that the last one? And there's another pin over here that's related to kind of enable and shutdown. And it's a bit of a massive pain in the arse to get these chips to operate without the whole circuit, you know, the whole feedback loop being complete. It's a pain in the arse. So if you are making repairs to the drive circuit, it's very difficult to know whether you covered everything or whether you fixed everything before you fit the MOSFETs and power it up. Fortunately for us, I have friends in the know, and I have been given a technique which allows you to power these amplifiers up and get these output chips to oscillate with the MOSFETs in place without building any rail voltage. Now, the way that these amplifiers are designed is so that with your input voltage to the power terminals here, that input voltage, for example 12 volts, not only runs on the power supply MOSFETs, obviously to build the rails and for the switching power supply, but whatever voltage comes onto here is also present by design on the single positive rail. Now, these amplifiers are single-ended, which means that they only have one single positive rail voltage, as opposed to a positive ground and negative rail voltage that you'll see in most half-bridge designs. These amplifiers use only a single positive rail that is then cut in half used as the half is used as a ground for the speaker terminals, so that the sine wave swings up to positive rail. 0 volts is kind of mid rail, and then negative is actually 0 volts. So this is just one single positive rail. And when the amplifier is in idle or is not powered up, whatever you have here going from your 12 volt or to 14 volt supply ends up on the rail to start with. And then as the power supply starts switching, that rail goes from 12 volts and then climbs all the way up to your 200 volt rail. Now this is fantastic because with this small modification, we can use only whatever we have on here as the rail voltage, and we can get the amplifier powered up and producing audio even just with this 12 volts as our rail voltage. So you can see how that makes life a lot safer and a lot easier when working on these amplifiers. Instead of the amplifier coming on and activating with 200 volt rails, therefore causing huge damage and explosions if anything is a problem, with a 12 volt rail, that is such a low voltage and there's such little current on demand that you can easily catch any mistakes, any things that are still wrong with the drive circuit. You can easily catch any problems before they damage any of the circuitry here. It's like I call it safe servicing mode. So this is the servicing mode modification that you need to make. Pay attention here. So in order to power these amplifiers up without full rail voltage, we need to trick the PIC chip, which is here, which controls the whole power supply section of the amplifier, into thinking that the full rail voltage is actually present, even though it's not. Now, usually, the way that this works is this chip will have a pin, which actually I think is the 4th pin along from this side, which is tied to this capacitor, and the chip will listen to the rail voltage. It will see, okay, how much rail voltage do we have? Do we have enough rail voltage to power the amplifier up and activate the output section? Now, usually, this voltage, obviously it's not listening to the full 200 volts. The voltage will be stepped down through voltage dividers. There's a 100k ohm resistor here that we have to remove for this mod. So this chip will listen to a tiny voltage, probably like 1.7 volts, which is a reduced version of the rail voltage through a voltage divider. And then it will say, yeah, okay, we're ready to go once it's got the right voltage on it. So in order to trick this chip into thinking we have rail voltage, we simply need to give it that small voltage which it thinks is actually rail voltage. So we remove the 100k resistor here. On this board it is labeled up as R, oh crap, there's a veer in actually that goes over the marking there, so I can't tell you what that is, but it's the resistor that is tied to the 4th pin along from this side. That's pin 14. So pin 14 will be tied to a 100k resistor. In this case, it's actually tied to 100k, which goes through this 10 ohm. So on this specific amplifier, pin 14 goes through this 10 ohm resistor, then to this 100k. So you need to remove the 100k or the 10 ohm. You just basically need to prevent the actual rail voltage from going through this kind of voltage division circuit to pin 14. So by removing either this resistor or this resistor, you isolate those. So now the chip is getting 0 volts on pin 14 because you removed this resistor. So now it's thinking, there's no rail voltage whatsoever. So obviously it's not going to turn on, even if the rail voltage was present. Now what you need to do is you need to give this chip the exact voltage that it would normally see with the correct rail voltage present. So to do that, we take a 5.6 kilo ohm resistor, which is just the right value to turn this pin here, which is 12 volts. This pin is the kind of VDD or VCC, which is going to be about the same as what you have on your power input terminal over here. So this takes our kind of 12 volts, passes it through this resistor, and then for ease of soldering, rather than soldering to pin 14, we can solder it to this capacitor here, C23. And there is enough resistance to ground to pull the voltage down from 12 volts through this resistor down to about 1.7 volts. And that tricks the chip into thinking that enough rail voltage is present to start the output section and get the amplifier up and running. The last thing you need to do is you need to remove the power supply driver. If you leave this in, then the amplifier will still generate the rail voltage. So what we've done here is we've tricked the amplifier into thinking rail voltage is present, even though it's not. So now we need to actually remove the rail voltage. And to do that, we just need to remove the power supply MOSFET driver. That will prevent the power supply MOSFETs from switching, which prevents rail voltage from building. So by simply removing two components, 100k ohm resistor and our power supply MOSFET driver, and just by jumping from VDD or VCC through this 5.6k ohm resistor to pin 14, the amplifier now, whatever state it's in, it believes that we have 200 volts there or thereabouts on the rails, and so it will turn the amplifier on fully and start the output section, which is perfect. So let's show you that now, and let's see how this amplifier acts with only 12 volts on its rails. Okay, so we've got our power supply hooked up. Let's just turn it on and crank that up to a normal kind of voltage. Just go for a nice round 12 volts there or thereabouts. And so with 12 volts going into the power terminals, without the amplifier turned on, nothing on the remote, you can see that we not only have our 12 volts here on the power supply MOSFETs, but we also have our 12 volts on the high side output MOSFETs. So that 12 volts is then passed on and becomes the bottom of the rail voltage, and then any additional rail voltage that's generated from the power supply sits on top of this. It doesn't feed it back to the power supply, obviously, but yeah, that becomes the kind of starting rail voltage point. And you can see here that if I probe the low side, which this should be 0 volts usually on a half bridge amplifier, obviously the low side drain we should have 0 volts, we actually have some voltage there. In this case it's 3.4 volts, so not exactly half of the 12 volts that we've got going in, but once this amplifier gets up and running, that does end up being about half rail. So as far as the output section is concerned, that does kind of become 0 volts. The half rail is kind of 0 volts. You can see there that we have that 3 point whatever volts on the speaker terminals as well. So that is ground as far as the output section is concerned, meaning that actual 0 volts, whatever over here is actually going to be 0 volts. So usually you would see negative rail voltage on the low side gate and source. Here we do actually have 0 volts, and as far as the amplifier is concerned, at the moment that would be about -3 volts. So that's the service mode modification. Now I want to show you how the amplifier acts and how to get it fully powered up, and even to a point where it produces audio whilst in service mode with only battery voltage being used as full rail voltage, removing that scary 200 volts. So firstly, I'm using 15 volts to get this amplifier up and running, and the reason I'm using 15 volts in the power supply is because due to how the output architecture works, 12 volts isn't quite enough to get this amplifier kick-started every single time. Now, without the full rail voltage there, the characteristics of how this circuit works are slightly different, and it doesn't kick into operation straight away without some external kind of input. So 12 volts wasn't quite enough to get it up and running every time. 15 volts or anything above 13 volts really is kind of the sweet spot, and the reason I'm using 15 volts I'll explain a bit later. It's to do with what I've got available with me right now, but anything above sort of 13 volts should be absolutely fine to get this amplifier up and running. Now if you just try and turn on this amplifier, you know, as it is, nothing else hooked up, just with 15 volts, ground and remote, let's see what we have. We're going to probe the low side drain. So obviously the low side drain should have a nice big square wave on it when the amplifier comes into operation. So let's go ahead and turn the amplifier on real quick by shorting out remote and positive over here. So just going to hit the remote now, and you'll see that initially it bumps up and then does a little pulse. So the amplifier is currently, you know, operational, it's turned on, but we don't have any output switching on either of the low side drains. If we turn the amplifier off and try again, boop. So it tries to come on and switch, but fails to do so. And what we're left with is a kind of half operational amplifier that is turned on, but not actually doing anything with the output section. Let's take a look at what the LEDs show. So guys, this is the LEDs on this amplifier. When you first turn the amplifier on, you get all 3 lights come on at once. This means the amplifier is in health check mode. It's checking the health of the amplifier, checking the rail voltage, and deciding whether it's safe to come on. So all 3 lights are on. And then what should happen is the orange and red lights should turn off, leaving us just with the blue one. The red protect light turns off, meaning that there is enough rail voltage present. The amplifier believes there is anyway. And it's trying to operate the output section. The orange clip light is present still though, however, because it detects that no output switching is happening. There's no output switching. So when the orange light is lit, that means that you have a problem with the output drive circuit usually. However, in this case, it's just that it hasn't been kick-started into operation. Because we're using such a low rail voltage here, as you can see, we have 15 volts on the power supply MOSFETs there, 15 volts. We also have on the output MOSFETs, on the high side drain, we also have about 14.5 volts. This is what I was saying about how this amplifier uses the input voltage from the positive terminal, and it uses that to form part of, or the base of, the rail voltage over here at 14.8 volts. So this is the only rail voltage that we have, and as a result this amplifier doesn't come on straight away. It needs kickstarting, and in order to kickstart this amplifier into producing output switching, we have to feed it with some RCA signal to kind of kickstart it into operation, kickstart the feedback loop, kickstart the self oscillation. So in order to do this, you're going to need about 2 volts RMS worth of sine wave. I've got 48 hertz sine wave going in with about sort of 1.82 volts RMS worth of signal voltage. So let's go ahead and plug that in now. You just want to plug it in. Make sure as well, it's very important that you have a load connected across the speaker terminals, because these amplifiers, they do not like oscillating and coming on without a load connected across the speaker terminals. Very important you do that at all times on these amplifiers. That goes for, to be honest, that goes for most Class Ds. It's good practice to always have a load connected to your amplifier if you are powering it up and idling it for any long period of time. So I've got a 16 ohm load hooked up to the speaker terminals, and I've got my signal going into the amplifier just here. Now I'm going to turn the amplifier on again with the signal going in, which should kickstart the amplifier into operation. And as soon as I see any signs of switching on the output section, I'm going to instantly remove the RCA, because obviously that will draw current as we have a load hooked up. So let's go ahead and hook up. Let's go ahead and turn the amplifier on, and let's see if that will kickstart the amplifier into operation with a bit of signal. Yep, there we go, and quickly remove the RCAs, and we have operation. So this amplifier is now up and running fully with output switching. Look at that, both sides of the amplifier, both sides of the bridge of the amplifier are switching now on the low side drain and the high side source, high side gate. Everything is working perfectly. And as you can see now on the lights, we have just the blue light lit, which means the amplifier is fully up and running, fully operational. So now, you know, if I applied the signal back in again and connected the speaker, this would produce audio. Even though we only have a rail voltage of, what, 14 volts on there. Pretty amazing. This is a complete game changer when it comes to working on these amplifiers, because now you can go ahead with the amplifier up and running and check all of these waves in great detail, and take your time doing so without any risk of the amplifier exploding, failing, anything kind of getting damaged, because you've got such low voltages in here that that's not an issue anymore. So yeah, we can go ahead and take our oscilloscope, make a start-stop function on these drive waves, and just compare and check that they're all good. They need to be exactly equal, all of these. Got the low side. This is the low side gate, low side drive on this side. Let's go over to the other side of the bridge and check the other ones. See, there's a slight variance there between this side and this side. See that, how that side is 10.1 volt RMS and this side is 9.6 volt RMS. There's a slight amplitude difference and also a slight dead time difference. So that's something that I might be looking at later on with this amplifier and seeing if I can get them to be the same, or see if, at the end of the day, this is basically two different amplifiers on the same PCB in internal strap mode. So there may be differences with dead time, with capacitor variance, tolerance differences with the capacitors and the timing and stuff like that. So it might not be an issue, but it's something for me to bear in mind. But yeah, this is an awesome state for the amplifier to be in for working on it safely and just making sure everything is good to go. So again, to recap, in order to get this amplifier up and running in service mode, remove the 100k resistor, remove the MOSFET driver for the power supply FETs, jump over from this VCC or VDD pad, which supplies 12 volts through a 5.6K resistor into pin 14 of the PIC chip. That will then trick the amplifier into thinking that full rail voltage is present. Then in order to get the amplifier up and running, you need something above 13 volts going into the terminals. Something between 13 and 16 is fine. And you need a little bit of RCA signal just initially to kickstart the amplifier, to kickstart the Class D switching into operation, which you can then remove, and the amplifier will then self-oscillate from then forward. Awesome stuff. That's freaking awesome. Now, this got me thinking. This is all well and good. You can repair the amplifier like this. You can, check everything's working okay, check drive waves, and make changes to diodes, resistors that are out of tolerance for the gate and stuff like that. You can do all of your normal stuff. Now the amplifier is up and running at least, and you can check everything is fine in a safe environment. However, after you've done that and you're happy with how the amplifier is operating in this kind of service mode state, the next thing that you can do is, well, the only option next is to remove the service mode and go back to 200 volt rails again. Now, in the situation that I'm in, where I've got some slight variance on the low side gate drive there that you saw, 10 volts versus 9 volts and slight difference in dead time, I would quite like something in between. It would be nice to be able to have control over that rail voltage, so that I'm not only running it at 12 volts or 14 volts, I can slowly increase it and see how it behaves on 50 volts or 80 volts or 100 volts before we go to the full 200 volt rails. Now, there is a way we can do this. Obviously, this amplifier is in a state where, as far as the control circuitry is concerned, the amplifier is fully fine and is functional. So we can start injecting additional rail voltage into the amplifier on top of the 15 volts or the 14 volts that's already there from an external voltage supply. If we have control over an external voltage supply, we can start increasing the rail voltage ourselves and see how it behaves on 30, 50, 80, 100 volts. So that's what we're going to be doing next, hooking up an external voltage supply to inject rail voltage into this board to make sure that it's fine with a bit more voltage in the rails. So here we have an old donor amplifier. This is an amplifier board that I don't have a heatsink for. It's never going to be run again, never going to be fixed. We did actually fix it. I think this is one of the ones we did on the live chat, fixes an amplifier. But I decided to take this board and turn it into what I'm calling my rail voltage supply board. So by doing this, what I've done is removed all of the output FETs and removed all of the rail capacitors and instead put in place some smaller ones. The reason for that is I don't want lots of energy stored in the rails. I just want enough capacitance there to smooth out the rectification. So just some small capacitors in the rail voltage location. So the idea of this is I want to be able to feed into my amplifier that I want to repair rail voltage, and I want to be able to fully control it from 0 volts all the way up to top rail. This amplifier is a half-bridge amplifier, and this is using 2 rail voltages, positive rail voltage and negative rail voltage. So, for example, with 12 volts going into this amplifier, I think we have something like positive 80 volts ground, negative 80 volts worth of rails. So that's a pretty good scope of voltage that we can go. We can go from 0 volts all the way up to 80 volts at 12 volts. Then if I increase my power supply voltage all the way up to 16, I end up with 116 volts. So I have plus 116, ground, negative 116. So I get about 235 volts across the rails at my absolute maximum. So the thing that I need to do now is I need to modify this amplifier in order to give me a full control from 0 volts all the way up to plus minus 115 volts. How do I do that? So what you could think to do is just just feed in different voltages into the battery terminals here. So the problem with that is that once it goes below a certain threshold, maybe like 8 volts or 7 volts, once it goes below that threshold, the drive circuit stops working, because this chip, this TL494 chip, which is actually controlling the power supplies, generating pulses, it won't work below a certain voltage. So that means that we can only really go from like 7 volts worth of input, which equates to perhaps, I don't know, 40 or 50 volts worth of rail. So our bottom point then becomes about 40 or 50 volts, and we can only go from there up to a full 115, 116 volts worth of rail on each rail. In order to make this fully adjustable from 0 volts, we need to have this drive circuit active at all times, regardless of what we have on the power terminals. So in order to do that, we need to feed this drive circuit with its own voltage supply, with its own power supply, separate from what we are feeding to the MOSFETs and the transformers. So in order to do that, I've just removed this little transistor here, which is the VCC transistor that supplies not only the chip with its 12 volts, it also supplies the NPN drivers with their 12 volts for passing on the drive wave to the MOSFETs. So by removing that, we can solder a cable and we can give this wire a constant supply of 12 volts, 14 volts, some decent voltage to keep this drive circuit active at all times. Once this drive circuit is active, we can then, starting at 0 volts, start feeding low voltage into the power supply MOSFETs and the transformers, and then that will equate to a gradual rise in voltage on the output rails. We're basically just stepping up voltage from nothing up to a high voltage. So I can then start at 0 and gradually turn up 1 volt, 2 volt, 3 volt, 4 volt, and that will equate to the voltage on the power supply MOSFETs, which will give me a gradual, adjustable, controllable increase in voltage on the rails. Now, obviously, because I'll be using up my bench power supply that I've got here for adjusting the input voltage to this kind of bare bones amplifier here, I won't be able to use this to actually supply voltage to this amplifier for all of the drive circuit, PIC, etc. So the idea is to use the same power supply for driving this drive circuit here as what we use to drive the rest of this amplifier here that's not the rail voltage. So in order to do that, I've just got myself a little spare power supply down here. This one's actually a 15 volt power supply, and the reason for that is that these amplifiers, to get the output section to kick into operation, you need a bit more than 12 volts on the output section on the PIC and stuff. So I've got a 15 volt power supply here. So all we need to do is just hook this up to the drive circuit here, to the VCC of the drive circuit, which is going to be on that transistor pad where I've got this wire soldered to, and ground, and that will activate this drive circuit, and then also run a wire from here up to the amplifier, the main amplifier power terminal, so that this amplifier also sees about 15 volts for all of the PIC and everything to work on this amplifier. So with our 15 volts hooked up to only ground and to the VCC for the drive circuit, on the MOSFET gate, we can see that we already have a drive wave. And that's because the drive circuit is now active. It's getting VCC to the TL494, it's getting VCC to the NPN drivers. So we have our MOSFET drive on the gates of the power supply MOSFETs. But on the drain of the MOSFET, we obviously have nothing, because we have no voltage going into the actual amplifier itself. We only have 15 volts going into the drive circuit. So the drive circuit is active and ready to go, but we have no voltage to drive. We have nothing to turn into rail. So at this point, then, we can take our variable voltage power supply and we can start increasing the voltage from 0 up. So we start at 0. Let's take a look at our MOSFET drain over here. And let's start increasing the voltage from 0 and see what we see on the screen. Ooh! So now we're at 1 volt, 0.8 volts on the power supply. And you can see that we've got 1.3, 1.2 volts RMS worth of drive on the power supply MOSFET drain. Bear in mind the drive wave looks like this. And this is the drain wave. So yeah, very, very small voltage. Now that equates to a rail voltage of plus minus 6 volts. So we already have plus minus 6 volts there on the rails, just from about a volt, like 1-ish volts worth of power supply wave. So we can keep increasing this, and we have full control now of the rail voltage. We can go all the way back down to 0, turn the power supply down, take a little while to sink down due to the small capacitors that I've got on there, but we can go all the way down to pretty much 0 volts on the rails, and we can start increasing it just by increasing the voltage on the power supply. So it's a very, very simple switching power supply circuit. We've just got a dual output voltage, positive and negative output voltage. So now we have plus minus 12 volts. This is going to be pretty useful perhaps for generating plus minus 15 volts if you need to test any drive circuits or any driver boards when they're not actually in the board. There you go, plus minus 15 volts. There you go, ready for you, or some op amps or something like that. Pretty useful. So now let's keep increasing this further. So we got 2.2 volts going in at the moment. Let's go up to, say, 6 volts. So with 6 volts going in, that equates to a rail voltage of plus minus 42 volts. Nice, pretty useful. Let's go back down. You can see there that we have full control all the way from 0 volts all the way up. Now let's keep going all the way. I'm going to go all the way up to 16 volts on my power supply here. See here, currently got 6.6. Let's keep going all the way up. 8 volts, 9 volts, etc. All the way up, still going, still going, still going, all the way up. 12, 13, 14, 15, 16. So with 16.3 volts worth of power supply wave, which looks like that on the power supply FETs, drive circuit now looks smaller than the wave obviously, we have rail voltage of plus minus 116 volts, giving us a total potential difference of around about, what's that, I don't know, 130 volts, sorry, 230 volts. Yeah, so there's 230 volts DC there of potential difference on this board now. So obviously, for using this little supply now that I made a little power supply out of this board, I can use this positive rail voltage, and I can inject that into our B2 amplifier over here. Now I probably could use the full 200, or you know, I could probably use the full potential difference between these rails if I wanted to, but it just gets a bit of a headache with getting that amplifier to see the negative voltage as ground as 0 volts. It's just, yeah, it's just a bit of mismatched nonsense with the grounding and stuff like that. I don't really want to have to do that because the ground on the B2 amplifier, the output ground is tied to the main ground, so then that would be a massive pain in the ass. So I'm just gonna use the maximum voltage that I have on the positive rail, 116 volts. That's more than enough for me to fully test the B2 amplifier with, you know, full control over the rail voltage. I can go up to 116 volts. Provided the amplifier works with 116 volts worth of rail voltage, it should be absolutely fine with 200 volts. I just didn't want to go from 12 to 200. I wanted something in between that I could just slowly turn up the rail and just make sure everything was happy before I go full 200 volts. So that's pretty dope. That is pretty awesome that I have this ability now to you know, create my own rail voltage and inject it into various different amplifiers. So now that you've seen how I am generating this controllable rail voltage, let's inject this into the B2 amplifier and show you how it works. So now then, all I've done is I've taken this little wire here, which is connected to the positive rail of the donor board under here, and clipped that onto the rectifier output for the rail voltage of this B2 amplifier. Now, this board is currently activated with the drive circuit, but I have 0 volts going into the power supply MOSFET, which means that we only have our 15 volts worth of voltage here on the power terminal, which equates to roughly 14.5 volts worth of rail. So let's fire the amplifier back up by kickstarting it with some RCA. Ding! There we go, amplifier's up and running. Now what we can do is turn on the main variable voltage power supply. We're going to hook this probe up to the rail voltage here just so we can get a DC look at the rail voltage on the scope screen here. So rail voltage currently is sitting at 14.2 volts and we have a 10.2 volt RMS switching wave on the output FETs. Now then, let's turn on the power supply, which is going to start increasing the rail voltage. So we're going to start down at about 2.3 volts. There we go. Now as I start increasing this, you see there the rail voltage is coming up. Oh my days, we've got 30 volts worth of rail voltage now. So gentlemen and ladies, if there's any ladies watching, definitely not, who the hell, anyway, what we have here then is we have an amplifier that is up and running, operational, and I have full control of the rail voltage. The minimum that I have control over it from 14.5 volts all the way up to 120 volts. That is pretty awesome, isn't it? That is freaking awesome. So that is a way to safely power these amplifiers up without a risk of exploding anything, because you can, I can monitor the current draw. Here we go. So this 0.7 amps, this is how much current this amplifier is drawing from the rails through this power supply board from the power supply. So 0.7 amps, that's nothing, is it? That's like fuck all. That's absolutely nothing. So we can continue to increase this rail voltage by turning our power supply up higher, which is going to in turn increase the voltage on the rails of our donor board and therefore increase the rail voltage of our amplifier. So now we have a rail voltage of 50 volts. So that would be like plus minus 25 volts. Yeah, looking pretty cool, looking pretty good. Everything's still good. We're only drawing an amp worth of current, so let's go even higher. Let's turn this down to 50 volt divide. Let's keep going all the way up. 63 volts, 70 volts worth of rail. Everything still looks good. Low side drain looks good. I'm pretty sure the drive waves are still looking a-okay. This amplifier is still operational with these higher rail voltages. Let's keep going. 86 volts, 90 volts, 100 volt rails, and at our maximum 16.3 volts worth of input we have 116 volt rails, and the amplifier is still functioning absolutely beautifully. Both sides of the half bridge to make a full bridge have good looking low side drain waves on them. So that's pretty awesome. Let's sink back down again now. Nice and slowly sink back down to a nice safe voltage there. There we go. So yeah, how freaking ballin' ass is this? We're injecting our own rail voltage into this amplifier in order to power it up slowly and safely and monitor everything along the way without risk of damaging our new expensive output MOSFETs. That's pretty goddamn awesome. Now obviously on this amplifier we're just using one of the rails of our donor board, our kind of rail voltage amplifier down here. We're just using the positive rail, but if I was wanting to repair a big half bridge amplifier that used both positive and negative rail voltages, I could also hook up the negative rail voltage to the board that I was working on, make some other modifications, and I could do the exact same thing to pretty much any amplifier. That will make, well, especially working on those great big Korean half bridge like 12Ks, they have a rail to rail potential voltage of like 550 volts with a maximum input voltage, which is really fucking scary. So that will make working on those things a lot easier and a lot safer. To be able to power the output section up with such a low voltage and just health check everything, make sure everything's working okay before allowing full rail voltage to be present in the board. That's freaking awesome, and I hope that you guys have learned something there from this. Now obviously the method that I've used to do this is quite janky. Using a spare donor board to generate voltage. Like, guys, I should really be using a bench power supply. I could do the exact same thing here with a proper bench power supply that, I don't know, goes from 0 volts to 200 volts. That would be the ideal thing, and then I don't need to use this janky amplifier to generate rail voltages. I could just use a proper bench power supply, which, yes, that would be the right thing to do. However, I wanted to, this was mainly as a test of theory. This was just to see if this actually was possible to do before I go spending £800 on like a decent bench power supply that goes from 0 to 200 volts with enough current to make this work. So that was the idea behind it. It was a proof of concept. I'm really happy that it works now. Although, to be honest, this works so well that why would I spend £800 on not only one bench power supply to go from 0 to 200, I'd need a bench power supply that also did the negative rail as well. So maybe 2 bench power supplies, or maybe one that does positive and negative. Like, I already have that here. Right here in front of me, I have that. So I don't think I need to buy anything else. This works beautifully. The only thing I would quite like is I would probably like to get another one of these, another thing similar to this, so that I have full control over not only the input voltage to the amplifier on the rails, but also the full control over the voltage going into the drive circuit for my donor amplifier and therefore also the power terminals of the amplifier that I'm currently working on. At the moment, I just have like a 15 volt spare supply hooked up, but I'd quite like full control over that, and I'd quite like it to be nice and clean as it is from this. So another 12 volt variable supply would go down nicely in the workshop. But yeah, as far as that's concerned, I don't need any other equipment. That is working beautifully, and I can apply this logic to pretty much any amplifier that I'm working on if I need to. Not all amplifiers are worth like hooking this up for. Like, you only really need to do this if you have an amplifier that you're not sure that you repaired correctly, you know, or amplifiers that you can't really check the drive circuit without the MOSFETs in place. The only reason really that this is something that I need doing on this amplifier is because I don't have a way to check the drive circuit properly without the output MOSFETs being fitted. Like, the drivers just don't come to life unless you have the FETs fitted. That's the thing. So that's what's required on this amplifier. I need a way to power the amplifier up with the FETs fitted, but without risk of damaging them. On most Korean half-bridge amplifiers, you can power up the drive circuit, check all the waves without the MOSFETs fitted, and that's fine. But yeah, good to know this is something you can do. I'll be making a separate video at some point going into the detailed repair procedure for these amplifiers. Obviously, I haven't actually gone over any of the repair procedure or any of the things that are worth checking that die a lot of the time in these amplifiers. I've just kind of talked you through how to put it into service mode and how to power it up on a low voltage safely. So I hope that was useful to you. Stay tuned if you want some more videos about how to really repair these things. And a big shout out to my man, I can't really say his name, but basically this modification here, this service mode mod, I was given this information by somebody that is an authorized Sound Digital repair guy. So obviously he was given that by Sound Digital himself, information as to how to get these amps powered up. I probably could have figured it out, but it's nice to be fed that information so that you can just go ahead and do it without needing to mess around and risk damaging anything. Like, I probably wouldn't have risked trying this modification out on such an amplifier that's so expensive and so high power, but obviously being told, oh yeah, just do this and do this, good stuff. So now I'm telling you, and hopefully you can put that modification to good use, either in Sound Digital style full bridge boards or using this information to, you know, repair some other amplifiers with different circuits, modifying it slightly and doing it how you like. But I'm really happy. This has given me the ability to fully check this amplifier out, see how happy it is running. These MOSFETs here are getting a little warmer than the rest of them, so that's something that I want to look into. This is the low side that is slightly higher amplitude than the other one, so I'm going to look into that slightly. It has a little bit more dead time than the other one, so I'm going to look into that a little bit just to see why these ones are heating up. I think it's just mostly this FET here. Yeah, it's pretty much just this end MOSFET here that's getting kind of warm. So, you know, I'm going to look into that, just see what's going on, see if there's any reasons why that one's getting hotter than the others. Either way, something that I can look into. But I'm very happy that I am able to take this amplifier, crank up the rail voltage all the way up to a super high value, slowly and gradually, without risk of blowing my new MOSFETs. Woohoo! 116 volt rails from zero, pretty much. Really awesome. Really freaking awesome to be able to do that. That is really awesome. Full control. Haha, love it. So yeah, guys, I hope you enjoyed, and yeah, stay tuned to the channel for more stuff like this and more live streams in the new year shortly, once I've got something interesting to actually live stream about. Take it easy, guys. See you in the next one.